we see is this, the physical PCB and the PCB assembly. So first 5-6 months will work because people take care it like a baby. And afterwards, when we go to mass build, suddenly things will go wrong because of people don't scale up properly, or what worked in the first 5 boards may not get translated to next set of boards. So these are the problems, and generally sometimes things go wrong because of assumptions. People assume things and they say if 5 things can be done, 50 things is only 10 times the cost and 10 times the effort. It can be even 100 times the effort when we are tuning it. So I'm trying to address all these issues one by one, how to control this like that. And yeah, I can open the slides and I'll start
Okay,
unraveling one by one. Yeah.
let's do that. And I'm actually I started streaming a little late than when I introduced, but again, once again, sorry for the delay transmission. I would say happy 2026, and today we have Mr. Ambaprasad with us from Silicon Valley of India, that is Bangalore, and we will be talking about the CTQ versus CTF conundrum in high-speed PCB designs. So let's start sharing the screen and let's get on to the actual discussion. And here we go. So we have here.
Full size.
Can you see our screen, everybody?
I can see the
Yes.
screen.
Okay, great. So let's start. And here we are, high-speed SERDES.
So high speed design, I went on telling since last 30 years. When we talk of high speed design, high speed is only in name. To validate and to render it and simulation, actual design and even manufacturing sometimes is not as high speed as the design is going to perform. So there's a lot of
Correct.
ideas get into that, lot of efforts. It's an industry by itself, it's a science by itself and engineering by itself. So here we have the roadmap for high-speed networking comparison. Somewhere 2006, we started at 25 Gbps. Now we are hitting, we are in 2026, 1.6 terabyte is under specification, which is most likely to become a reality in 2027 or a little earlier, depending on the market conditions. And then again, the plans for the 3.2 terabytes and 7.2 terabits. And here, very interesting thing, here again, you see, we say how long it takes. The first jump took 6.5 years. The next took 5 years. Next 3 years. I mean, if we go with the same scale, the next jump should happen not in 3 years. It can happen in 2 years or 1.5 years. And again, there's a lot of philosophy here. The Bohr says it is difficult to make predictions, especially about the future. And again, Bayers say the number of people saying Moore's law is come to an end, which is not true, but Moore's law is now getting translated into packaging. People are solving Moore's law by packaging and not by silicon scaling. Yeah, go to next slide, please. Yeah, here this is some sort of a pin map of a 3.2T LGA module. A lot of power supply rails are there, 1, 2, 3, 4, 5, 6. From 12 volts input to 0.7 volts, we have so many rails. It has been color coded very nicely. We can see the color wherever we have the power supply pins. And we have, again, there is an electrical protocol, there is the optical protocol, then the 400G and 800G two modules. And again, it aligns with the cable. There is a RF region, 0.9 mm by 0.6 BGA ball pitch, LGA in this case, land grid array. And again, we have a low speed region where we have a 0.6 by 0.6 pitch. This exactly fits into what we called as earlier in our episodes as a high density interconnect. can go to next slide, please.
Yes, already did.
So here I'm showing when we implement this kind of modules in a server class PCB, how it looks like. It is just some schematic. It is a theme actually, not the actual PCB. We have shown a ASIC at the center, and then we are fanning out, and all these fan outs have to be length matched. Actually, this type of PCBs are used mostly in AI, especially AI backend. These are used to 224 Gbps right now. People are rendering it, but it may get into 448 Gbps in another year or so. So limitations are in ASICs, PCB and PCB connections, cables. These are the limiting factors. So maybe in the next episode, I can show the actual physical length, how we reduce the lengths so that we have a better throughput. What exactly happens is when the speed increases, the physical length which it can propagate also reduces actually. What could have been a rack will become a server blade, and what would have been a server blade may become a small PCB, and what would have been a small PCB can become a device by itself. So this is how things are scaling. They're scaling in the other direction. Yeah. Industry collaboration, there is IEEE is involved, the designers, IEEE and cable companies, connector companies, and again simulation and validation, EDA companies are involved, and test and measurement. Test and measurement plays a very important role. Yeah. Next slide, please. So, okay, when we try to, this is just hypothetical. This is going to be in 2027, first half, or it can be 2027 financial year first quarter, or a calendar year first quarter. So when we try to implement this kind of high-speed channels in a PCB, obviously it is CTF, critical for functionality. The PCB does not function, no point in even deploying it. So, okay, considerations, why 448 Gbps is hard and why. So there are a lot of what we call side effects which will come into picture. Just a minute. So you have, okay, one is 448 Gbps channels we are running. Power, it consumes, these are the byproducts. Power will be power. They can be density. They can be data rate is going to increase. Latency is a problem. Reach is an issue. Reach, I told how we control that. Maybe in the next episode I can show. What would have been a rack may become a PCB. What would have been a PCB can become a device. Then critical timing issues, architecture, NPO, CPO, people have to use. And I can assure you one thing, the byproduct is a lot of power consumption and a lot of heat and signal integrity issues and emissions, EMI, AMC problems. These are the byproducts. Yeah, next level. So we have architectured a system, let's say, and now when we define the actual schematic into the PCB, we use what? We use vias, we use traces, and we use power plates. These are the three. With using these three, any PCB can be architected. So they can be a stub when there is at the connector level. Because of the trace routing, there can be crosstalk issues. And again, there are other issues like a return loss and insertion loss. And again, now there are two issues here. So with this, our signal integrity simulation ends, pre-layout and post-layout. Then we get into the reality. The reality is it has to be manufactured, and with all is said and done, this PCB is a mechanical object. The mechanical tolerances play a very important role. That is what we told as mechanical challenges. And again, we are telling about manufacturing challenges. These mechanical challenges and manufacturing challenges, where CTQ is going to raise its head. Till so far, we are CTF. when we are in a layout stage. But when we go to manufacturing a PCB, assembling a PCB, the mechanical issues will come. That is where the CTQ will raise its head and we see the conflicts. Next slide, please. Yeah, this is just a PCB interconnect. How PCB, we are shown a hypothetical something like a 20-layer PCB stack up we have shown, and we can see though the via in the vertical direction will become like a stub. It has to be controlled by back drilling or something, and there can be a return path. Ground vias have to be there, and in this type of PCBs, almost 50 to 60% of the vias are going to be ground vias, which are even passive vias. They are not active vias. Actually, they are used only for ground stitching, and as a return path, they are going to be there.
Okay, great. Let's take a quick break here, then we'll come back.
Yeah.
We'll continue the presentation. Good morning, good afternoon, and good evening, and welcome back if you are just logged in to Global Electronics Friday Talk Show with your host, Rajiv Kulkarni. We bring this talk show every Friday, 30 to 45 minutes, discussing about various topics that is involved in the electronics manufacturing activities. So today's topic is CTQ versus CTF in the high-speed PCB designs, and we have Mr. Ambaprasad, who is an expert in the PCB design, and he has been in the industry for the last 40 plus years. Let's continue our today's talk show after this small break. Yes, Mr. Ambaprasad, let's get back to our...
Open the screen. Yeah, good. Let's stay here for some time. Go back, one slide back.
Okay.
Yeah. So unless we are exposed to very high-end EDA software in simulation, most of the layout designers will see via only in X and Y direction. They won't see the vertical direction. So that is this puts capacitive and inductive parasitics. This has to be properly modeled. Very high-end CAD packages are able to do this. So this issue more or less is resolved, but again, it has to be resolved. And again, there is going to be some gap between what we have simulated and finally what we get manufactured at the PCB level, because the PCB itself has got some tolerances. So especially when we talk about 224 Gbps, even a tolerance of 0.05 millimeter can act like a discontinuity of a huge magnitude. So it's very good. We should have a very tight budgeting and a very tight tolerancing. So the budgeting is CTF, tolerance is CTQ.
Okay, great.
So CTF, I told CTF first because functionality is taken care in the design itself, critical to function. The characteristics essential for the product to work as intended by the engineering team, derived from functional requirements, safety and regulatory. So many times when we go for regulatory, even they ask for a schematic. They check the schematic also, the safety part of it, regulatory part of it. They check the schematic, they check the layout, and they check the live board also. So then what we projected in pre-layout or a pre-manufacturing, there can be some few dBs of leakages can be there. So that has to be fixed. We may have to go for a second rev. So that's it. Then impedance control on a high-speed backplane, connector mating force, thermal dissipation via structural integrity is very, very important. And breakout region. So this breakout region itself, I can have one session, and there is so much of idea to talk about that. Maybe we can do it a little later, sometime. Let's go to the next
Excellent.
slide.
I think this is
Now
it.
let's assume the PCB is fabricated and it is assembled. Critical for quality issues will come. They even come at a TQ stage, a technical query stage. Characteristics that directly impact the customer's perception of quality. And here the customer is, we are the customer now. So the designer is the customer. The PCB fabricator is the supplier. Derived from a voice of the customer and translated to measurable specs. Surface finish, signal integrity, budgeting, EMI compliance, cosmetic appearance, reliability matrices, and PCB fabrication and PCB assembly attributes. So these are all very tightly controlled and very top tier EMS houses and PCB fabricators uh, with a proper NDA in place and with a DFM and DFA handshakes while the design is happening, a concurrent engineering, they can address this very easily. Easily said and done, but it takes a lot of effort. And then it is frozen and it becomes a part of the digital twin. That's how it goes. But yeah, it is solvable. It's nothing impossible to solve, but we should have very early engagements with our supplier. Here, a window shopping will not work. What I mean is, whomever we deal with, we have to persist with them. So we cannot
Correct.
deal with one person and say, assume that it works, and to do cost cutting, we go to another vendor, then both of us will be in a big trouble. Yeah, next one. Next.
Quality.
Critical to function, critical to quality. High-speed design attributes, critical to quality. I think this way, yeah. Now the characteristic that directly impact this we are covered actually. We have to go to the next slide actually. One more slide.
Not this?
Conflict, next slide. I am showing in a blue color.
This is what it is. This is the last slide.
Here
Yeah.
I have just tabulated where the conflicts will occur. Tolerances versus manufacturability, I just told that maybe what our tolerance we are told is too tight to manufacture. It looks very, I mean, when we go for a quotation stage, everything is, yeah, people say, yeah, we can do it, sir. And then when they see the actual data, suddenly they find that it is too difficult and there is a price or a time penalty for that. So that is where things will start becoming little, I don't say, I can in a very, with all humility available to my exposure, at my exposure, I can say the fiasco will start happening. The honeymoon stops and the reality starts biting. Okay. Then there is a quality priority. There is a CTF priority. An example is bezel alignment as far as the socket is concerned, and material selection. A customer demands a particular material, and the PCB fabricator may say they are happy with some other material. But this is more or less solved because now, when we go for a design kit, even the ODMs, device manufacturers are telling which material we have to use. So that way, some people have started thinking very early. The shift left is happening here. So this is more or less solved. And signal integrity versus aesthetics, smooth plated finish for quality perception. Now, all the R&D is almost stopped in PCB material. Now a lot of R&D and effort is happening on copper finish. because when we say 144 Gbps, the skin depth is even less. Any defect on the copper surface, let's say it is higher than the skin depth, we are going to have problems. So that's it is. Then choosing copper roughness for high-speed traces. Reliability versus cost. A customer wants a low cost as usual. Function requires redundant vias, thick copper and exotic connections. What I told by redundant vias means so many ground vias we are putting. To just act like a return path and act like a heat sink or whatever it is, thermal vias. So suddenly one person say, why there are so many ground vias? They are not connected anywhere. Why you have to put so many ground vias? Whether you put one ground via or 10 ground vias, they are connected to ground. If you put one via, connection is over. Then why you are putting a second and third and fourth via? These are the questions. And again, aerospace class 3A builds where redundancy is non-negotiable. Why I told aerospace is not using this kind of speeds right now. But why I told aerospace as an example is they're very good in reliability issues. The reliability, the way they solve reliability issues is very good. Even the people who do very high-speed designs and all should learn from them. Conflict management, conflict resolution, standard, even if we take a deviation, they do a thorough exercise and document everything. That's where I find it is very good. And the compliance versus customer preference. A customer wants everybody wants a small design. The design has to be as small as possible. It has to have a very small footprint. Okay. Otherwise, things are becoming bigger and bigger. If you want to make it robust, it has to be bigger. If you want it to slick, it has to be smaller. So this is where the conflict starts. But this is more or less solved because all these standard bodies like PCA, SIG or somebody, they have defined everything. They have defined the connector, they have defined the assignment, they have defined the chassis width and the depth and the height. Mostly this kind of architecture, people go for a 2U type of a height. They can do in 1U, but they're going for 2U because of thermal issues. 2U is very easy to cool. Yeah, you know better. Okay. And function requires spacing for creepage clearance as per IPC and military standards. Still, in the power supply region, we want more space. We want more gap. Okay. And the power module creepage distance versus compact fan factor. These are the issues. So next slide, please.
I think we are done with
No,
this.
there is only one more slide.
No, we don't have.
Yeah, how to resolve? Next slide. This is the last slide. It's taking some time to. Yeah. Okay. So resolutions, how to resolve this CTF versus CTQ conflicts. Traceability matrix, map each requirement to its source. Functional spec, yeah, there are design kits and assembly kits and material kits are available from the vendor. They call it as a 3DK. Earlier we used to call PDK, ADK and MDK. Now they call it as a 3DK. All the three are one. You cannot take away one from the other. It's a perfect, you can say it's like a Mercedes symbol. Perfect. There are three proper regions. Then risk-based prioritization. Use analysis to weigh customer dissatisfaction and functional failure. Class level standards. Yeah, my favorite subject, the standard companies like IPC, JEDEC, military standard, aerospace standard. They have got answers for everything. And again, trade-off. A trade-off means maybe you want to deviate. That is where the gap analysis come into picture. People want to deviate. Yeah, they can deviate with a thorough homework after that. Then tired rule libraries, separate CTQ-driven versus CTF-driven rules. In the DFM, they can be resolved and reconcile overlaps. So whenever you put a rule, two things we have to remove from the rule. One is what we cannot implement, we have to remove, and redundant rules. I don't want to say everything again and again and again. So that has to be, if you remove redundant rules and unimplementable rules, at least in the current revision, the number of rules becomes less. When rules are less, people follow it. If rules are more, people act they are following, but they don't follow. So there is a difference between these two. Okay. So this has to be reasonable. Design reviews and with dual lenses. So the designer should know manufacturing, and the manufacturer also should know a little bit of design. So ensure both quality and functional stakeholders sign off. That's it. Now, this is just the beginning. And we see when we get into breakout region and differential trace configuration and stack up,
Great.
more things will unravel. So that's how it is. I
Great.
think we have taken only 1 minute extra. That's
No,
good.
no,
Our
no,
time.
no problem. We have a couple of questions here, which I would like to read out, if that is okay with you.
Yeah,
And
no problem.
so, thank you very much for the wonderful presentation, Mr. Ambaprasad, about CTQ versus CTF. One is, how do you prioritize CTQ versus CTQ in your design practices?
In the design practices, CTF is non-negotiable.
Okay.
There is no point in designing which is not functional. That's very clear. So CTQ, I told earlier, even the PCB fabricator, or at least at the PCB fabricator at the CAM level, and even those who negotiate at a stack-up level, they should also know a little bit of design. I don't say they have to be designers, but they should know this where we belong to.
Right.
Okay. The best example is 10% tolerance versus 7% tolerance. Why 7% tolerance? Mathematically speaking, 7% tolerance does not overlap between 100 ohms, 85 ohms, and 90 ohms. But if you go for 10% tolerance, all the three can come in one bucket. So people
Correct.
should understand, especially at the PCB. But the realization has come. People are understanding this, at least at the CAM front end, and those who negotiate the pricing, they know that. And even the FEI is from a PCB company. They are understanding this. This is happening, but it is happening at a tier 1 PCB vendors.
Tier 1, yeah.
It has to just come down. And again, the designer also should know a little bit of the pain points of a PCB manufacturing. No point in speccing and designing something which cannot be manufactured. So there has to be some, there is some gray area over here. But the person whoever has questioned this can contact me directly. No problem. My number is available in the public.
Yes.
I'll be able to solve it case by case. I can
Sure.
address this issue. Yeah.
Okay. And one more question is, what tools or methodologies help you balance these aspects?
Tools and
CTQ.
methodologies,
Yeah.
EDA, even when we buy EDA software,
Yeah.
for example, Cadence is very good because they were the early, they implemented this long ago. They have a lot of tires. I mean, they have a high-speed plugins, high-speed license that will solve the problem. But again, RF plugins will solve the problem. And again, even in the EDA world, a lot of acquisition and mergers are happening. A lot of companies. Actually, the problem is the co-simulation, the package simulation, the PCB simulation, and even the simulation for a cabling and all is a must. All connector companies, they are able to give you the, I told earlier, 3 DKs, PDKs, ADK, and material DK. These, maybe I can address them how it is done. These are very important. This has to be done even before the schematic starts. Okay. Yeah.
Okay. I think these are a couple of questions we had. And again, thank you for answering that. And thank you all the people who have watched the show and who are going to watch the show. And so we will come back next week with a different topic, which is basically we are talking about AOI in electronics assembly and manufacturing. And we have another industry expert for that. And in the meantime, we will continue with these other PCB design related topics with Mr. Ambaprasad in the later sessions in our other episodes. And once again, if you are not subscribed our channel yet, please do subscribe. because the more the subscribers, more the viewers, and more the viewers will make our guest happy, and also the sharing of our this particular knowledge based podcast would definitely help. So Global Electronics brings every week this show in order to share our wealth of knowledge, our guest wealth of knowledge, I would say, in the electronics manufacturing industry. So please do share our channel link and request you to subscribe. With that said, once again, happy 2026, and wherever and whichever part of the world you are based, please do take care and have a wonderful weekend. Thank you, Mr. Ambaprasad. Thank you very much.
Yeah, thanks. Because your next topic is going to cover CTQ issues, because the assembly houses tier 1 have jumped into AI using AI at the back end and all. This is some of the CTQ's problems are going to be solved. So again, the questions, thanks for the questions. The questions they have asked, 3 DKs can be covered in one session, not an issue for me. See you sometime. Happy 2026 to all of you,
2026.
and happy 2026 for the industry. Thank you.
Yes, thank you very much. Thank you. Appreciate your participation.